This next assignment is a doozy, so let's get it rocking. We're doing heat loss and gain, and these are the things we're going to take a look at. So go ahead and add this to your notes, that thermal conduction is the process of heat transfer through a solid by transmitting kinetic energy from one molecule to the next. So that's when it's transferred directly through a solid member. Thermal convection is heat transmission by the circulation of a liquid or a gas. So this is with hot air is kind of moving from one place to another. That would be an example of thermal convection. Radiant heat is transmitted as rays, waves, or in the form of particles. So if you have a wood stove or something over in the corner of your house, you may have heat radiating from that. You may have radiant heat from that, and that could be another form of heat transfer. Heat escapes through walls and openings when the temperature outside is lower than the temperature inside. So we would have heat loss through walls, windows, doors, and the roof. So the structure requires additional heating due to the heat loss and incoming infiltrating air. The same thing could be said for summertime, where you have heat trying to enter into maybe an air-conditioned building through these same members. So that's your summer heat gain, and that is referred to again as heat gain. And you can get solar heat through walls, windows, doors, and roof. There's also occupant heat, which is about 250 BTU per hour per occupant. And in the next slide, I'll show you what a BTU is, or 715 BTU per hour if the occupant is exercising. Cold mass heat gain is from equipment such as computers, coffee makers, lighting, or things like that. And again, lighting is also heat gain. So a BTU is a unit of energy in the United States, and it's defined as the amount of heat required to raise the temperature of 1 pound of water, which is about 2 cups, by 1 degree Fahrenheit. So a person can produce, again, I'm going to go back, a person can produce 250 BTU per hour per occupant. So people actually produce a fair amount of heat, and you've probably experienced this if you've ever been to a concert, or if you've ever been to an assembly or something like that with lots of people around, or even in our classrooms occasionally, if there's lots of people around or moving around, it gets noticeably warmer in the room, even if you're just sitting. Fahrenheit is a common temperature scale used by engineers in heating, ventilation, and air conditioning, which is commonly referred to as HVAC. And BTUs per hour is a way of measuring the heating power of a system, such as a furnace or even a barbecue grill. So you would use BTU per hour to figure out how big your furnace needs to be. 1 watt is approximately 3.4 BTUs per hour, and 12,000 BTUs per hour is referred to as a ton in most North American air conditioning applications. So you would buy an air conditioner that might be a 2-ton air conditioner, or a 3-ton air conditioner, or 1-ton air conditioner, but it's all based off BTUs per hour. So it's a lot of different unit conversions. Make sure you note those down, and when you do your conversions and calculations, you're actually going to figure out how many ton air conditioner that you need and how many BTU furnace that you need, because that's just what's common in residential construction. So British thermal units, R value is a measurement of thermal resistance used to indicate the effectiveness of insulation. So the units for R value are feet squared, hour, degrees Fahrenheit, per BTU. The units are really not as significant here as just an R value number. Typically things are we just talk about it in R value numbers, because this is a mouthful to say this. U value is a coefficient of heat conductivity, and it's a measure of flow of transmittance through a material. And so it's essentially just the inverse. So what you need to know is to calculate U value. You take the R value and you do 1 divided by the R value will give you the U value. 1 divided by the U value will give you the R value. So note both of those in your Google Doc, or even take a screenshot of this to help you with that. The formula for heat load is Q prime, and that little dash means prime, equals AU delta T, where Q prime is the total cooling or heating load, so that's what you're going to solve for, BTU per hour. A is the area under investigation in square feet, so that might be like your whole wall, the square footage of your wall, as it's a rectangle. It's like a sheet of paper if it's horizontal there. And then the U is a coefficient of heat conductivity. So you're actually going to find the R values. We have a chart of R values, and you're going to take 1 divided by the R values to get your U coefficient of heat conductivity. And delta T is the difference in temperature between the outside and inside. And so you can find that using a chart. We're going to use the chart for Denver. So here's an example of that. And this is actually what you're going to need to do in your assignment, is calculate total heat loss and heat gain through a wall. So this wall has no doors or windows. It's 8 foot by 12 feet, so the area is 96 square feet. The wall R value is given right here, all these specific values. So I'm going to show you where you're going to find those in your assignment. Here's our assignment, and the place that you're going to find that R value is down here at the bottom. And so I've put a quick link to it. I've also, as I scroll up here, I've also put the R value chart right here, because this is actually the steps required, or the steps explaining how you're going to put your R values in there. If we click on the R value chart, then we load up our reference chart here, and this is where you're going to find all of the R values. So if you're looking particularly for the gypsum wallboard or drywall, it says it's 0.9 per inch. But if we go back to our image or our drawing file and zoom in, you're going to see that the gypsum drywall is only 1/2 inch. So since it's only a 1/2 inch, then that means my R value is only 0.45. So make sure that you multiply this R value by the number of inches that you have, unless it's per unit, in which case you just use this as whatever number is given. So if we continue on, that's where we get our R values from. And we have a total R value. If we sum them up, we do U is 1 divided by R, and that gives you your U value, and this is the value that you put into your worksheet. So now we're going to choose the nearest location using our data for Denver. And where you're going to find that is in this assignment, average temps for Denver can be found here. So if we open this up, and it says use a 97.5% dry bulb summer and 2.5% winter values from Appendix D, minimum and max temps in Denver. So we go to Appendix D and go down to Colorado, and then you can look for 97.5%. That'll give you the temperature and the dry bulb summer. So for Birmingham, Alabama, which we don't care too much about for our project, your winter temp would be 21 degrees, which means that 97.5% of the year it's above this temperature. It's warmer than this temperature. 2.5% of the time it's going to be colder than this temperature, but we are not designing for that 2.5% because otherwise you're over engineering. It's too expensive. So we're going to put these as our temperatures, 94 and 21. So your change in temperature, your delta T, is your design temperature of 68 degrees, and for that Birmingham, Alabama option, if it's winter, we would design that for 21 degrees, and the summer temperature, I believe, was somewhere around in the 90s. So that's what your design temperature would be. Your delta T is the difference between these, so we would subtract those. So for that wall example we had before, we had an area of 96, our U is 0.074, our delta T, we subtract those from the inside design specs, and then the outside 97.5% temperature, and we get a Q prime of 462 BTU per hour. We're going to have to resolve this again for that other temperature, that summer and winter different options, and that's going to give us a different Q prime. So that's what you're going to need to do for your assignment, and you'll figure out the total Q prime, or the total heat loss and heat gain for summer and for winter. If you'll see number 3, which is really where you're going next after you watch this, is read all directions. It's really important that you do that. So I'm going to load up the transmission load worksheet, and that looks like this. So it gives you instructions for how to make a copy of it. You're going to put in the R value for each wall, and you find the walls and what they look like in your example utility shed. So that link is here. I've also quick linked it to the bottom, the shed drawing file and the R value chart. You can get to those in either place. When you load this up, you're going to find something like this. I'm going to click to zoom this in just a little bit, and here it shows all the different walls: east, west, north, and south. So the west wall and the north wall have no windows. Calculate the area of this wall and subtract the area of these windows. And the reason that we do that is because you want the area, total area in square feet of just the wall. Doors have a different area and the windows have a certain area. So what you're going to do on the south wall is figure out the area of the wall and subtract the area of the door, and that will be what you put in for the south wall. Then you'll add the area of the door right here. You put the area of the door here, and then that total will come out over here. So you have each component listed in here.